Hi, my name is Johanna Mathieu. I'm an assistant professor in electrical engineering. And I'm going to tell you about my research to support renewable energy integration using flexible electric loads and storage. So this is a general overview of my research areas. So in general, my goal is to improve the sustainability, economics, and reliability of the power grid. And to do that, I develop algorithms to coordinate resources in the network, such as energy storage and flexible electric loads. So you might have heard of demand response, so we're using some concepts from there. And the goal is to help integrate renewables, specifically wind and solar, which produce power whenever they want to produce power, not necessarily when we want them to produce power, so they're a challenge. And in particular, I'm interested, instead of building lots of new storage, I'm interested in harnessing the existing storage in the network. There is some small-scale energy storage that exists. There's not a lot of it in terms of batteries and things like that, but there's a lot of storage in thermal storage, so in buildings, refrigerators, air conditioners, things like that have storage. So just a brief overview, this is what motivates my work, so the challenges and opportunities in modern power systems. So the main challenge is we want to integrate all of these renewables, but they produce power that looks like this. So this is a solar power plant producing over the course of a day, and a wind power plant producing over the course of a month. And you can see it's producing whenever it wants, and this is particularly hard for the power system to integrate, where we're used to controlling generators that produce when we want them to produce, like coal power plants and natural gas power plants. There's also load growth that power engineers are coping with because of electrification of vehicles, and I very much support that, but it's causing stress in the system. The network is aging. There's parts of DTE systems that are 100 years old and haven't been upgraded. So we're dealing with a lot of different challenges, but fortunately there's also opportunities because there's more sensors in the system, more communication systems. We have better situational awareness of what's happening in the system now. And then we have more opportunities to control different resources that might exist, small resources. So what I mean by that, controlling distributed energy resources. So in my research, I like to look at problems where we're trying to control very small resources like refrigerators, air conditioners, and so forth, so that they operate normally. You don't notice that they're being controlled, but we're exploiting the fact that they have some flexibility in terms of when they consume power. So the main goal is turning their uncontrolled power consumption into something that looks a little bit different. So we want that blue line to track that black line, and that signal could, for instance, be the output of a wind power plant. So we want to consume power when the wind is producing, as opposed to having the generation follow the demand. So we develop control algorithms to control when these resources are consuming power in a way, hopefully, that's not noticeable. So we call this type of control non-disruptive control. Like I mentioned, these resources already have a lot of flexibility in terms of when they consume power, and we can leverage that. So your air conditioners and refrigerators, they cycle on and off. So you hear the compressor turn on in your refrigerator, and then it turns off for a while. So basically what it's trying to do is keep the temperature within a range. But because it's not holding the temperature to a very specific target value, but it's within a range, that means its power consumption is flexible. So that's what this is trying to show. It cycles on and off, and normally a refrigerator, it's not working. Okay. Maybe it's just delayed? Okay, sorry about this. I'll just try to get it all up there. So normally a refrigerator is consuming, the refrigerator heats up, and then it switches itself on, cools down while it's powered, and then switches off again. And this is what its power consumption looks like. But what we can do is maybe turn it on a little bit early. If you get a big gust of wind in the system, turn the refrigerators on a little bit early, and then when that gust of wind goes away, turn it off a little bit early as well. And that type of control allows us to coordinate lots of different resources together so that they can basically track the outputs of variable renewable generation from solar and wind. So in my work, what I do is I develop controllers, optimization approaches, estimators to understand what's happening in the network, and so forth. And what we're trying to do is do this in a way that's low cost, privacy preserving, not impacting consumers in any sort of way, not affecting the milk in your fridge. And we look at different cases to say, if we have different levels of information or control about the system, how well can we perform? So these are cases just showing how well we can track the output of a wind power plant with a bunch of loads. In this case, air conditioners trying to track a black signal. And you can see if you know a lot about your system, you can do really well. If you know a lot less about your system, you don't do as well, but it's still okay. And we develop the algorithms to let you do okay in those sorts of cases. These are other thrusts of my research. I work on a lot of different problems. In particular, the second one here is relevant to campus. We're using University of Michigan buildings, modeling them as thermal batteries and trying to use them to provide services to the power system, specifically integrating renewables. Thanks.